Hi everyone, I am Kunshik Lim from the Distributed Computing Lab. Professor Young Ik is my advisor. Our work on SWAM, which solves memory contention and increases user responsiveness in embedded systems, was published at the premier Mobicon conference. Today, I'm glad to present this work to you all. Swarm tries to address the essential issues of memory contention which reduce application performance on resource-constrained embedded devices. Our novel solution has demonstrated promising outcomes after through the testing. I'm looking forward to discussing the essential ideas and insights underlying Swarm, and I appreciate your participation in this presentation. The increase in RAM capacity of smartphones over the past decade has led to an increase in application capacity and the opportunity for more concurrent applications. As a result of that, despite the increase in RAM capacity, some users complain that application launch times and application response times are still slow. Even with the large RAM capacity of flagships, real-world users have found that after using the smartphone for more than 13 days, the response time of major applications increased by 1.9 times. Manufacturers are making efforts to collect and analyze data from smartphones through big data platforms. Over the past decade, the price of mobile devices has dropped from $30 to $5, and along with that, memory capacity has increased by the effect of 16 from 512 megabytes to 8 gigabytes. Despite this, subspace has also increased from 512 megabytes to 3.5 gigabytes to compensate for the lack of physical memory. This shows the steps for reclaiming memory pages on the Android mobile platform. As illustrated in the diagram, it adopts the swapping and killing mechanisms by utilizing GRAM and the swap device. The steps are executed in the following orders: GRAM, swap, LMKD, and OOMK. OOMK and LMK were enabled since 2008 year. GRAM and swap were enabled since 2014 and 2016, respectively. The striped gray bar indicates that the swap operation is not activated if there is available GRAM space when both GRAM and swap are enabled. LMK has been replaced by LMKD since 2018. The table refers to the OOM score, memory threshold, and group name of applications that can be killed by LMKD. Existing swap and OOMK will be used in mobile environment, even though they were being used to solve the same problem in the mobile environment. They were not cooperating with each other and causing problems with application launch time and user responsiveness. From three observations, such as response time, memory usage, and initialization delay, we developed this swarm to integrate the two mechanisms and to solve the memory shortage problem in our software approach without any hardware method. The operating system supports two main process killers to free up available memory space. The first is low memory killer daemon, which is a daemon that removes the process at the user level to free up memory space. The second is out-of-memory killer that kills memory-hungry processes at the kernel level that have not been used recently. In this study, we observed the four factors affecting the performance of mobile applications from our observations on Android devices. Observation 1 showed that impact of swapping on the response time are not negligible, and an effective swapping mechanism is more important in modern mobile devices. And observation 2 showed that efficient memory space management is needed not only to support a decent level of the user experience, but also to keep up with the platform service. And observation 3 considering that the SO symbol lookup cost is not negligible while most applications do not share the SO files, it is important which type of SO files to select both as a victim for swap out or memory reclamations. And finally, 4 shows that the XML processing cost is not negligible anymore in mobile devices because the XML files of mobile applications tend to become more complex nowadays. We found that 119 AIM-free applications are installed by the manufacturers when the smartphone boots up. We observed 1.7 times UI lag at the start of the swapping behaviors and when the swapping space was full. OOMK triggered frequently and the UI lag increased to 2.6 times. We also found that even on high-end smartphones, OOMK was triggered after 19 days of booting. This page shows the observation 2. The Android platform allows background application to run. This background application runs without any interaction with the user. The behavior of these background applications and other consumed 31% of the 8 GB of memory. Figures that run in the background have a significant impact of platform service. This page shows the observation 3 about the SO symbol lookup cost. Out of the 60 most popular applications uploaded to the Google stores, a surprising 58 applications do not share their SO files with other applications at all, meaning only 2 applications share their SO files with other applications. Even if SO files are not shared, there is always a cost for symbol navigation, so it is important to deal with the cost of SO files effectively. And we observed the XML processing cost for 15 popular applications in the Google stores. We observed that 12% of the total time was spent translating the UI layout and 88% of the time was spent drawing the XML data into GPU memories. These XML UI costs increased as the UI complexity of the application increased. So, especially, we measured how much time the SO symbol navigation and XML processing cost. We observed earlier actually either into the application launch time. We found that games like Cookie Run and Angry Birds have a a large number of SO symbols, and complex XML UIs. This page showed the overall system architecture of Swarm. Our Swarm designed to improve our responsiveness. Swarm consists of three main components, such as adaptive swap, OOM cleaner, and OOM killers. The design goal of Swarm reduce application response time and start time by combining the GRAM and swap, and reclaim memory pages based on the program properties and access patterns, and finally delay the terminating application as long as feasible by estimating launch time. We designed Swarm to orchestrate swapping and killing mechanisms to enhance the three performance degradation described at the previous pages. The first, adaptive swap in blue, dynamically controls the swap space to improve memory shortage. Second, OM cleaners in green proposed a novel memory reclamation technique to obtain free memory without forcefully terminating the application. Third, UM killer in red calculated as all the such as symbol lookups, XML characteristics to improve the initialization time of modern mobile applications. First, adaptive swap dynamic allocated and release swap space. It allocates SO pages that are less frequently referenced and accessed by applications as swarm areas. For these behaviors, adaptive swap created dynamic swarm files at the file system level. Adaptive swap combines the GRAM region with the swap space and then the region with the swarm files. SO files used by the platform are allocated to the GRAM region because of their frequently called property. SO files used by applications are allocated to the swarm region because they are not accessed by other applications. The adaptive swap supports modern memory unmap operations to speed up large swap out operations. For example, when performing a large swap out operation, we can dynamically adjust the minimum free unit of the memory space, as shown in the algorithms on the right. Okay, let's see the second component, OOM cleaner. It supports two erasures. First, the SO eraser removes SO pages in the GRAM that have become marginally shared. Second, the ISOP eraser removes pages that have been unused for a long time after being swapped out. Finally, the third component, EOOM killer, performs the same behavior as a conventional OOMK. However, it takes into account the new characteristics of modern applications such as SO symbol lookup cost and XML UI processing cost, and calculated them at the time of OOMK to eliminate the application with the lowest restart cost. This is very important in order to consume the less system resource such as CPU and memory when restarting. Here is an evaluation result. We implemented the prototype of Swarm based on the Android 12 and Google Pixel 6 with EUFS 3.1 stage. Our experimental goals for SWAM are as follows. First, in comparison to a regular system, how much do each of the components that make up SWAM have handled memory resource? Second, how well does SWAM with each three components perform overall on mobile devices? These results are from an experiment on adaptive swap over SWAM. After conducting an aging test for 1 month, existing devices experienced a drastic drop in available memory capacity just 9 days after booting the device. However, our adaptive swap maintained over 600 megabytes of available memory even after 29 days. This page shows the experimental result for the second component, the OOM cleaner. We observed that the amount of swapped out pages reclaimed by the OOM cleaner was the most efficient compared to the existing swap schemes. We showed the experimental result from the third component, the EOOM killer. The EOOM killer resulted in far fewer post-application terminations compared to the existing swap mechanisms, such as this the experimental result. We experimented with the effect of integration of the three components of SWAM. We found that the number of terminated applications was significantly improved compared to the traditional swap mechanisms while evaluating 411s. In this graph, we experimented the amount of time that a user waits between clicking the application icon and seeing the burst screens. We got the 36% improvement in application launch time on flagship devices compared to the existing system. In this graph, we experimented the amount of time that a user had to wait between the touching a specific menu in an application and seeing a result. We got a 41% improvement in application response time on flagship devices compared to the previous system. Now, let's talk about the limitation of our SWAM. In this page, the orange numbers in the figures indicate how much SWAM space is reduced by SO erasure and ISOP erasure. In theory, SWAM can consume a lot of storage space to free up space in memory. However, SWAM systematically reduce storage capacity issues by preemptively freeing up storage space each ISOP erasures. So this is unlikely to happen in real-world environment. This is a trend graph of research papers on freeing up memory between 1999 and 2021. The statistics show that with the replacement of hard disk to SSD based on the NAND technology and advancement in storage I/O such as eMMC, eUFS, and NVRAM, there has been a steady increase in the number of research papers on swap in mobile devices, starting in 2013. This showed that swap is an important keyword to ensure consistent and predictable user responsiveness and application launching speed for users when memory path is reached in mobile device environment. While OOM is a strategy that frees up memory without the user permission, swap seeks to free up memory without killing process by temporarily storing the contents on or secondary devices. However, structurally, swap suffers from I/O overhead and render lifetime issues. As a result of that, there is a growing body of research on swap to address these issues on mobile devices. Existing researches has focused on pre-processing techniques that need to be done in advance to optimize application performance on mobile platforms. Specifically, the ASAP, Acclaim, and Fast Track papers focus on system memory, and the Marvin and Smart Swap papers focus on random storage only. This research, on the other hand, perform both swapping and killing operations simultaneously, enabling the fine-grained and efficient memory management on mobile devices to reduce application execution time and response time. In summary, existing research over the past decade has focused on obstacles, Swarm focused on opportunities of system. This page shows the application launch time and response time, which are measured for user interactions with each application. Our Swarm improves application launch time with 38% and application response time with 44% from our test scenario. Let's see the video demonstration of Swarm on a real smartphone. The mobile environment, RAM size, and working conditions used in these demos are all the same. The first video will show an improvement in application launching speed, such as KakaoTalk. The second video will show an improvement in application response time, such as MP3 player. So far, let's summarize our research papers. We highlight the structural limitation of the traditional swapping and killing mechanisms which operate independently. We propose a new memory management techniques that allow two existing opposing memory management mechanisms to act as a unified memory management techniques. The experimental results show that it dramatically improves the number of the burst termination, application launch time, and response time. Thank you all for your kind attention and for listening so patiently to my presentation so far. I really appreciate you taking the time out of your busy schedule to be here and engage with our research work. Your presence and interest in our study truly mean a lot to me. Thanks.